Okay, so today we're going to be talking about different behavior of waves. Okay, so the first thing that's important about waves is that we have a principle of superposition. And what superposition means is that you can add or subtract these waves. So if I have a wave that's this high, and then I'm adding another wave that's this high, so if I have a 4-foot wave and a 6-foot wave, I can end up having a 10-foot wave. So we're going to be able to add waves just like we do with anything else. Another definition here is interference. So this is going to be that two waves can come into the same spot at one time. A lot of times you can't have two things that occupy the same space together. And in waves you can, so that there's interference, they come together. Okay, so this is the physical interaction of two waves coming together. So an example would be if you ever have an opportunity to sail from the Pacific Ocean into the Atlantic Ocean down in South America, they come together, and the waves from the Pacific Ocean and the waves from the Atlantic Ocean actually come together, creating a very turbulent sea area. And so that's a really good example of superposition and interference. Each one on their own isn't very destructive, the waves, but when they added together, when you come along the tip of South America, these waves become extremely large. And so what happens is they're just added together, and so they're much larger than each of the individual waves. So here's an example. There's three types of interference that we're going to be dealing with. One is constructive interference, the other is destructive interference, and then complete, we have missing an E here, complete destructive interference. So constructive, meaning they're coming together, they're going to be added. Destructive means they're going apart, we're going to subtract them, and then we're going to talk about complete destructive interference. So the first thing is constructive interference, and a good example of this is the wave situation with the Atlantic Ocean and the Pacific Ocean. So if we have a wave coming in here heading this way from, say, the Atlantic Ocean, and another wave heading this way from the Pacific Ocean, and the Pacific Ocean is much more passive, Pacific Ocean, it's much calmer, so the waves are smaller. Well, when these waves come together, what happens is they actually add. So we have this one right here is here, and then we're going to add this one on top of it over here. And so what ends up happening is these two waves come together, creating a larger wave. And all we do is we just add the amplitudes. So if this has an amplitude of 4 meters and this one has 2 meters, our new one's going to be 6 meters. Now the interesting thing about these waves is once they have constructive interference, they keep going the original way that they come. They don't hit each other and bounce back. They actually hit each other and go through each other. So this small wave continues going this way, and the large wave continues going that way. And so you can see that we're going to add these two. They're going to come together, they're going to add up, and then they're going to keep going the same way that they came. And this right here is what's called interference. And it's constructive because they're both in the positive side and they're up. Now we're going to talk about destructive. So we're going to have one wave that's going up and one wave that's going down. And as they come together, what's going to happen is you're going to take this wave and you're going to subtract that. So if this was 6 feet tall, say a 6-foot wave, and this is a 2-foot wave, we're going to end up having a 4-foot wave in the positive direction. Now it could go the opposite way as well, where your larger one is the underneath one. And then the same thing with the constructive interference. This small wave continues going this way, and it's the underneath one, and then the larger positive wave continues going that way. So this is what's called destructive interference. And then our last one is complete destructive interference, and this means that this is, say, a 2-foot wave, and this is a 2-foot wave. They come together, and they're actually going to complete nothing. So we have 2 positive and 2 negative, which will be 0. And then once again, they can complete going that way. Now this is an example of sound canceling headphones, if some of you guys have that, as well as sometimes airports, because the noise is so loud, we have very large, what they do is they produce, the planes or sometimes helicopters actually produce a sound wave that is somewhat equal and opposite, and so it ends up being not so loud. And if you live in the pathway for Patrick Air Force Base, you can hear some of these helicopters have a lower hum than the old-fashioned ones that did not have this destructive interference sound in them. Okay, so now we're going to talk about different waves that have boundaries. Okay, so we've just been talking about waves that went on and on forever, so the wave would just continue on downward. Well, now what happens if we have a boundary? Well, we have two types of boundaries that we're going to talk about. One is a free boundary, and the other is a fixed boundary. So the free boundary would be kind of something tied around a pole, and it could move up and down. So this is free to move. This knot over here is free to move up and down. And if I were going to be taking kind of like a jump rope, as you were a kid, you would tie it against maybe a pole and jump rope. If you were going to tie a jump rope around a pole and then you were going to create some waves by going like this, what's going to happen once it hits this boundary? And this is a free boundary. So we have a wave that's coming in here, and we call it an incident pulse or an incident wave, and it's the initial one. It's going to come here. Well, when it hits the pole, that wave is going to kind of be incorporated into the knot, and the knot is going to move up. So this is our original position. The knot's going to be moving up along this pole, and then it's going to just kind of bounce right back through here, and then the pulse is going to go back. So this is what's called the reflective. It's the one that comes back, and incident is the one that's going towards. So as you can see that this is a positive pulse going towards, and then this will move up, and then it'll move back down, and you'll create another positive pulse going in the opposite direction. Now we're going to talk about a fixed boundary. So this might be like a jump rope tied around a doorknob. So what's going to be happening there, or something that's fixed and unable to move. So here, if I take a flick to the rope, this incident pulse is the same over here, but once it hits this border, it can't move up and down. So what happens is it's reflected. So it'll bounce back, but upside down. So this is a positive pulse. It's going to hit the boundary and it's going to flip itself. It's called a reflected pulse. So the incidents are the same. This is a reflected pulse, and this is a reflected pulse. This one flips because it's fixed, and this one is allowed to increase and go up and down along the pole, and so it ends up going the same way. And I'm going to show you some examples tomorrow in class so you can actually see what I'm talking about here. Right now, just know that there are two different types of boundaries. Okay, and now our last thing that we're going to talk about is what's called a standing wave. And a standing wave is just a wave pattern that results when two wave patterns of the same frequency, the same wavelength, and the same amplitude travel in opposite directions. Okay, so an example of this would be if you put like a guitar string. That would be a good example. Also, if you had like a rubber band around a box, and once again, I'm going to show you some examples tomorrow, but if you flick that rubber band, you're going to see kind of this vibration back and forth. And so this is what it looks like. It kind of looks like a spaceship or a watermelon, but each of these are the vibrations of the string. So if I were to take a string and flick it, it would go bounce back and forth, and so this is what you're going to see. And this is just the motion of this string going back and forth and back and forth. And then if we could go back, the standing wave is going to be able to jump into two standing waves. And once again, I'm going to show you some examples tomorrow in class. But we could actually have it where it's two of these things vibrating, and we can also go to three, and we can actually go higher too. And I'm going to show you some examples tomorrow. What you need to know about these standing waves, though, is there's 2 points that we are very familiar with. We're going to talk about nodes and antinodes. The nodes are just any place where the standing wave maintains zero displacement. So over here on the fixed side, this node can't be moving up and down. And over here where your hand is, it's going to be moving up and down very little bit, but not very much over here. And then over here, this spot and this spot, this isn't going to be moving, it's going to be staying still. And over here it's staying still, and same thing with these three over here. And then we have the antinodes, which are basically the opposite of the node, and this is where it maintains maximum displacement. So the string over here is going to be maximum displacement along these, and these are what's called the antinodes, and then once again here, here, and in these 3 spots here. Okay, so don't forget to do the assignment, and tomorrow I'm going to have a lot of examples that I can show you what we're going to be talking about here. It's kind of hard to demonstrate in a lecture, but we'll do some hands-on playing with some springs and oscillations tomorrow. Have a good night, and we'll see you tomorrow in class.